Come in and see. Whenever you want, brother. Alright. I'm giving you these. There you go. Here's the new chapter, notes. Okay. As you probably are aware, and you've noticed about second semester, what have you noticed about second semester?
It's harder.
It's a little bit easier.
It's a little bit more difficult.
I don't like it.
No, I'm serious.
Anyways, this chapter is probably the most difficult one up to this point, as you probably can figure that out. Heavily math intensive, but also fairly conceptual. Today we're going to be doing all conceptual stuff, and we'll get into some of the math stuff later. Push through, guys. It's fourth quarter. I know it's really easy to just kind of coast out in fourth quarter, but just continue to push through and do your best. And I will continue to try to do my best in being available for you and teaching you guys the best I can. I'm not going to try to. I know it's even hard for teachers not to kind of shut down a little bit at the end, but I try not to do that. So this chapter is all about thermochemistry. If you were to look at those two words that make up that, you probably could be able to figure out what this particular chapter is discussing. What's thermo? What does that bring to mind? Temperature. Okay, temperature, heat-related things. Energy in the form of heat, all of that stuff. What are you doing there, Gage? So here's what thermochemistry is. It's a certain section of chemistry, as you can probably imagine, that specifically studies the transfer of energy during chemical reactions or phase changes. Okay, what's a phase change? Okay, solid to liquid. What phase change is that? Melting. Okay, there's a certain amount of energy that's required to change a solid object into a liquid object. We're going to talk about the energy involved in that. There's a certain amount of energy that is required to go from a liquid to a gas. The amount of energy that it takes, we have a name for that. We describe that with a couple definitions you'll see in this particular chapter. Right? So, first thing, quick review. We've talked about these two definitions in 2 chapters at least. Okay, if you remember, temperature was the average amount of kinetic energy. Remind me what kinetic energy is. Movement energy. And we talked about how solid, liquids, and gases all have movement energy, right? Even though we look at solid gas, it's still what? Moving at a subatomic level, it's more vibrating. Okay, liquids have the ability to flow, and so they can move around each other a little bit more. And gases have enough energy to break the what? What's the word? Chapter 11, the whole point of chapter 11. What are they breaking? What kind of forces? Intermolecular forces.
Okay. Who made the unit for heat, KJ? KJV.
Oh, great. I can't wait till he takes it next year.
Oh no.
All right.
Unless he doesn't.
So, heat, if you remember, we said we know that heat is being transferred from hot to cold if we see a temperature change. Okay, one way to know heat is being transferred is if you see a temperature change. If the temperature is not changing, you do not have heat. Okay? And it's the amount of thermal energy that's within one object being transferred to another. We say heat is being transferred. Okay? Quickly, we did talk about this last chapter. I want to make sure that we refresh our memory on this. Okay?
I like that.
Breaking bond requires that?
What did you say?
I said the definition, but
That's exactly
in an angelic voice, according to the music.
Alright.
Okay, choose to Spotify ads.
That was
Don't play this cause
All right, there we go.
Anthony.
There we go. Bonds breaking require energy. Now we talked about this. I'm going to quickly show you an example I showed you last chapter. We're going to try to make it quick here. Why do things bond? They become stable. What does stable mean from an energy standpoint? Low energy. So that would we would assume then that this would have high energy, right?
Yep.
And this would have low energy, correct?
Yep.
All right. So breaking bonds requires energy. Forming bonds, we said, releases energy. Okay. So what we're doing here, these are high energy weak bonds. And these are low energy strong bonds. Okay? So if you look at this, the ones that have high energy are weaker bonds and are easy to break. Okay? The ones that have low energy are stronger bonds and require more energy to break. So let's say if I'm going reverse. Let's say I'm going from low energy strong bonds. Okay? Would it take a lot of energy to break the bonds or a little bit of energy? A lot of energy. So I'd be putting a lot of energy in to get from low energy to high energy. Going the opposite, doesn't take a lot of energy to break weak bonds, and the formation of strong bonds gives off a lot of energy. And that's why we go from high energy to low energy. Okay? Every chemical reaction involves breaking bonds and forming bonds. Everybody hear me? Every single chemical reaction. There will be bonds broken, the atoms will rearrange, and bonds will form. Okay? Now listen to me very carefully on this. This is important. We've talked about exothermic and endothermic, correct? What does exo mean? Releases energy. Endothermic means? Okay, now listen. If more energy is required to break the bonds than energy is released in forming bonds, will it be endo or exo? If more energy, lots of energy to break bonds, and little energy in forming bonds, is this endo or an exothermic reaction? Endo. More energy coming in than going out. Endothermic reaction. The net gain of energy will be coming in. If it's the opposite, if little energy is required to break the bonds, and a lot of energy is released in the forming of bonds, what will that be? Exothermic. Which one's the more stable of the two? Exo or endo? Which one is going to be the one that's going to result in more stable ending? Exo, because, right? Stable means low energy. And if you go from high to low, where does the energy go? Out. If we go from low to high, where does the energy go? In.
Yeah, for real. What?
It's an inside joke from senior trip. Not something I'm talking about right now. Alright. Okay. So breaking bonds requires energy. The stronger the bond, the more energy it takes to break. That should make sense. So that's just showing, representing that that's a weaker bond, that's a stronger bond. Alright. Okay, I've already talked about forming bonds releases energy. And as you might have already anticipated, the stronger the bond formed, the more energy is released. Okay, I've already talked about this. Can I move on past this?
Yep.
How about this? Everybody good? All right, quickly, you should be all be able to answer this.
One.
Breaking bonds always what? Requires energy. Okay, exothermic reactions.
2.
Release heat. A reaction of nitroglycerin exploding is probably what? Why do you think it's exo?
It's exploding.
Energy is being released, right, in
Not
an exploding reaction. All right, here's the main vocabulary where we're going to see this whole chapter. It's called enthalpy. Okay? It's, yes, and just wait, and later on in this chapter we'll talk about entropy. Okay, so just like molarity and molality were very similar, but slightly different. Enthalpy and entropy sound very similar, but they're actually quite a bit different. Okay? This is the most important vocabulary word of this chapter. It says a measure of heat contained of a system at constant pressure. Okay? It's pretty complicated when we start getting into the idea of constant pressure and what that means. I'm going to simplify this for you. Anytime you hear the word enthalpy, think of heat. You might want to write that down. Anytime you think of enthalpy, think of heat. So if I have delta enthalpy, which you'll see in a sec, enthalpy is actually abbreviated with an H. That's the symbol for enthalpy. What does delta mean? Change in. So essentially when you think of the change in the enthalpy, you're thinking about the change in the heat, or the amount of thermal energy being transferred from one, either into the system or out of the system. Okay? And that, just quickly, what do you think a negative change in H tells you about the reaction? Okay, it loses energy. What kind of reaction do you think it's called? Exo, if it's losing, right? Releasing? Okay? Well, we'll talk about this later, but a negative change in H is going to mean exothermic. A positive change in H, energy is coming in, or heat is being transferred into the system, endothermic. Okay? All right, we will talk about, I'm just kind of giving you the vocab here. There is a thing called a calorimeter. It's basically where they do chemical reactions to figure out the enthalpy of something. Okay, it's actually quite unique. For example, I know you don't know a whole bunch of stuff yet dealing with calorimeters, but if you know the mass of the water, the specific heat of water, and you can measure the temperature of water, what you can do is, if you were to drop a really hot rock into water, eventually the rock and the water would come to the same temperature, right? Right? You would eventually reach thermal equilibrium. Okay? Well, if you know how much energy the water gained, that could tell you exactly how much energy the rock lost. Does that make sense? And so they can do chemical reactions in a calorimeter and study the changes that water has due to energy either being given off to the water or taken in because of what the chemical reaction is doing, if it's exothermic or endothermic. And we will do these math calculations a little bit later. It's just done in what's called a calorimeter. So it's used to figure out the enthalpy changes, or essentially the what? The heat. Okay. Guys, just showing you all the stuff. I'm not too worried about that. All right, we've talked about these two words. I'm going to go over them again here, and we're going to do a heating curve, and I'll show you where all of these things are. Yeah, I'm pretty sure I talked about this like 2 chapters ago or a chapter ago. Didn't I? At least reviewed it?
With phase changes.
With phase changes. Yep. So what I'm going to do is, I'm going to do another heating curve up here. Do you have any space for a heating curve anywhere? Okay. All right, so I'm going to set up a heating curve because I'm going to start showing all of what sensible heat is and what latent heat looks like on a heating curve. Okay, so let's just do the simple water example because we're all familiar with that. So let's say that's -20. Okay. Okay, here's your temperature. And this would be energy added over time. Okay? Now I know that my bottom little x-axis there isn't super straight, but Okay, so each of these vocab words that you're about to see are important in identifying and understanding what's going on with energy, and it can be used graphically to show on a heating curve. I'll actually make that line a little bit better. That drives me nuts. It's really hard to draw straight lines though. Is that okay?
That's better.
Everybody got this in? And we're going to actually fill in a lot of this here. I'm going to say what parts of the graph relate to sensible heat, what parts of the graph relate to latent heat. We'll talk about the phase changes and what the energy of those particular things are called. Okay, first and foremost, what phase do I have in this part of the graph?
That's frozen solid.
Solid, right? Okay, we're talking about water, right? What happens below 0 degrees Celsius? Solid, okay? So we know we have the solid phase. What about here?
Oh, that's liquid.
And what about here?
That's gas.
So what do you think I have in both these spots? What do you think's here?
Both.
During the phase change, you have both. I will have solid and liquid at this point, and I will have liquid and gas at that point, but we'll get more into that in a sec. Okay? So, here is the two types of heat that we have talked about, and if you remember, I said that one of them makes sense. Why did I say one of them makes sense?
Because it's sensible, you can see.
I mean, normally when you think about adding energy, for example, if I add energy, what do we normally think happens to the temperature? Okay, but how? How does it change? Go up or down? If I add thermal energy, okay, your temperature's going to go up. And if I remove thermal energy, what's probably going to happen usually? Temperature's going to go down. Okay? That makes sense. It's what we experience. Not many of you guys boil water and put a thermometer in it and check the temperature. Anybody ever done that? Yeah? Okay. Believe it or not, when you boil water, the temperature remains approximately 100 degrees Celsius. But Mr. Kramer, aren't you continually adding heat, right? If you have it on the stove, you're still adding heat or adding energy to it, right? And usually we think adding energy means the temperature is going to go up. But what you'll find is when you boil water, the temperature of that boiling water never goes above 100 degrees or never drops below. It approximately stays constant. Well, okay. What is the energy doing? Breaking or forming bonds. Okay, if you're going from a liquid to a gas, are you forming bonds or breaking them? You're breaking them. And what are the bonds called that you're breaking? Intermolecular forces. Okay? If I'm going the opposite way, let's say I'm going from a liquid to a solid, here the energy is being absorbed to form the bonds. Okay? Now, let's look at, on these curve graphs then, or on this graph up here, what areas represent sensible heat, or areas where we see a temperature change. Do I have a temperature change here?
No. At the curve. Oh, yes.
That's temperature change. What kind of heat is that?
Sensible.
Is this the sensible heat section?
No.
No? Okay. Is this the sensible heat section? How do you know?
Because you see
Got slant.
Temperature change. Okay? How about here? Okay, that's going to be called latent, yes. Sensible. Okay, so we've got our sensible heat. Is anytime you see a temperature change, and yes, if you looked at a graph, it would be where you have a what? Okay, what's that called in math?
Slope.
A slope. Okay, it's getting warm in here. I can see some people are trying to drift off on me.
It's very dry.
Okay?
What? It's dry.
and I gave
Why are you so red?
Okay? Latent heat. Where's the latent heat?
On the flat area.
Okay, so we got latent heat here. And we have latent heat here. Latent heat is going on when you're going through a what? Phase change, and we know when we go through a phase change, energy either going in to break the bonds or is being released in the formation of bonds. Okay? So, latent heat is when we do not have any temperature change.
Did you cross the first one?
This one?
Yeah.
It is, it's just not very good.
Layla.
Okay? Now, here we go. We have our change in H, which is essentially change in what?
And volt.
Heat.
Heat. Okay, the amount of energy. Okay? Alright, you're seeing the word molar. What do you think that represents? Oh my gosh, you guys.
Freckles.
Why are there always moles?
Alright, so. This is called, it says molar enthalpy of fusion. A lot of times, since we said enthalpy represents heat, we could call it heat of fusion. This is the amount of heat added to a solid. Where is it added at?
Melting.
So what do you think fusion represents?
The solid in
Melting.
okay.
So essentially, what the enthalpy of fusion is how much energy per mole you would need to apply to a substance to get all of it to melt. All right? Where would this be represented on the graph?
0.
0 degrees. So this latent heat is change H of fusion would be the amount of energy needed to convert all of the solid to a liquid per mole. Okay? Now, do we always have 1 mole? No, but could we do stoichiometry to figure out how much, if I had half a mole, how much energy I would need to break half a mole of solid water? How about if I had 14 moles of solid water? Could I figure out how much energy I would need to break 14 moles of solid water if I knew how much energy required to break 1 mole?
Absolutely.
Yes, absolutely. Okay? Now, if I'm going the reverse, here's an important connection. Okay, this isn't by melting. Okay, first up, melting, does that require energy or give off energy?
Why?
Requires energy. And so what you're going to find is the fusion will usually be positive, or always be positive. But if I am freezing, this is important, guys, for you guys to make this connection, right? What I'm about to say is really important. The number that is required to melt is the same number as required to freeze, except for it's being released instead of absorbed. Okay? So let's say it requires 150 kilojoules per mole of energy to melt an object. If I had the same amount of that object, how much energy would be required to freeze that object? The same amount, it's just it would be given up because now we're forming bonds. And what do we know forming bonds does?
It releases.
Releases energy, right? Everybody following with me? So this point here, solid to liquid melting or liquid to solid freezing, it's the same amount of energy just coming in or going out. Does that make sense? So if I asked you a question and I said, it required 250 kilojoules of energy per mole to freeze, okay, or to melt, I should say. How much energy would be released in freezing that much?
Whatever you just said.
Okay. All right. This is just saying that it's latent heat, so what doesn't happen? No temperature change. This is your typical unit. It's going to be in kilojoules. We know joule is our energy unit. It's been a while since we've done energy, but just a quick refresher. Okay? And it says same amount of energy as 1 mole of liquid freezes, just different sign. All right. We should know what vaporization is, right? What phase change?
Liquid to gas?
Yeah. Vaporizing. Okay, remember when we talked about vaporization, we broke it up into 2 categories. We said evaporation or boiling. Okay. So that would be, probably shouldn't use this marker. This is going to be the change in H of vaporization. which is essentially how much energy would be required to break liquid bonds to form a gas. Okay?
Is it the same thing, vaporizing is positive and condensing or whatever it's called?
Yep. So great distinction that Maddie just made. When you're vaporizing, because you're breaking bonds, energy's taken in. And it should make sense. Which one's the higher energy, liquid or gas? Yeah, so you'd have to bring in some energy into the liquid to get it to turn into a gas, right? That should make logical sense. Okay, and the opposite then, if you had gas and you wanted to go to a liquid, would you be gaining energy or releasing it? If you went from high energy to low, you'd be releasing it. That's why, typically, when you're going from a liquid to a gas, it's a positive change in H. And we're going the opposite, where you're condensing the gas, it's going to be a negative energy being released. Because I'm going from a higher form of energy to a lower form of energy, and the energy has to go somewhere, and it goes out. Okay, is that it?
Yes.
Pretty much, it's just saying it's latent heat, okay, measured in the same units, and it's the opposite sign, but the same amount if you're condensing. All right, and this is just showing what I have up there, and we're done, right?
Yeah.
That's where it was supposed to go. Let's go for it. All right, perfect. 4 minutes, pretty good.
Changing.
Hold on, Bob, I'll be right there.
Natalie, did you see how much like the former